All right, hello everyone. This is going to be a level 2 physics paper, 2023 mechanics external that I'm going to go through today. As ever, when you get to the start of a question, make sure you have a go on your own first. Use the video to help you or to check your answers when you're done. You need a pen, pencil, calculator, usual stuff just in case, and we'll get straight into it. So, question 1. About a softball match. We are told that the following diagram shows a layout of a softball game. We got a series of bases, and we are told that a stationary player accelerates from home plate to first base. The player takes 6.61 seconds to get to first base and arrives moving at 5.45 meters per second. Show that the average acceleration is 0.825 meters per second squared. Now, with these sorts of questions where you're given different sorts of times, speeds, acceleration stuff, those motion quantities, I always suggest just straight away writing down your D, V, I, V, F, A, and T, and just going through and filling in what you do know already. Now, we're going to be trying to work out our acceleration, so I'm going to leave a question mark there because that's what I want to find out. My time was 6.61 seconds. They arrive moving at 5.45, so that's our final velocity. And we are told that while they're at the home plate, they were stationary. So I know it's not a number, but I should have underlined it because it means that our VI, our initial velocity, is 0 meters per second. So now, and I want one of those equations of motion from our resource sheet that does not involve D, that does involve VI, VF, A, and T. And if you have a quick look, you should see that only one fits the bill. VF is equal to VI plus AT. Now we want to rearrange for acceleration. So I want to get the A on its own. So I'm going to take away VI from both sides and then divide both sides through by T. Divided by T, sorry. Equals A. Then I'm going to substitute those values in. 5.45 minus 0 all over 6.61. If you pop that straight into your calculator, you get an answer of 82450 meters per second squared, and I'm going to round it to the desired answer by 5 here, rounds the 4 up to 0.825, and that's the final answer. Now, if you ever get a show that question, remember to write your unrounded answer first, then round it to whatever the given answer is. And remember, even if you don't know what this answer is, the reason it's a show that is because you're more than likely going to use it in a subsequent part. So just remember to flick back to look for this sort of information, because chances are you will be using acceleration at some point. Okay, or you may have the option to at least. For part B, sorry, I should have said, for doing all this correctly is an achieve point. For part B, we are asked to calculate the maximum displacement between home plates and first base, and then part 2, explain why this displacement may be different from the actual distance travelled by the player. So for VI, again, we're going to work out the displacement between home plate and first base. I'm going to write down my 5 letters, VI, VF, A, and T, as before, but this time I'm trying to find displacement. Now, it's always good practice to never use an answer you've calculated in a subsequent question unless you really have to, or unless it's a show that question, in which case you know that this is the right answer, because there's always a small chance that you make a mistake and you don't want your errors to compound upon themselves. Often there are error carried forwards, but we'd like to get the right answer where possible anyway. So always try to use values given to you by the exam. So my VI is going to be exactly the same as before, 0. My VF is 5.45. I'm not going to use acceleration, even though I've showed that it's true. I'm just going to stick with these numbers instead. Now, I want to work out my distance. I have d, vi, vf, and t. I need an equation that involves all four of those, and with no a, that equation is d is equal to vi plus vf over 2 multiplied by t. Now on your formula sheet, it's not written with the brackets around it. Just be careful that the t is multiplying everything in this fraction, not just the vf. That's why I've used brackets here, just to make sure when I use my calculator later on, it does do the operation I want it to do. My vi is 0, so I'm going to just substitute everything in, divided by 2, all times by 6.61. I'm going to pop that into your calculator, and I'll get my answer. 5.45 divided by 2 times 6.61. And that gives us an answer of 18.01225 meters, which rounds down to 18.0 meters, or just 18 meters. Now, if you do that, that's enough for achieved in part B. The other way to get achieved is to just answer part II correctly. If you answer both part I and part II correctly, it's merit. Now, for the part II, why might this displacement be different from the actual distance travelled by the player? This comes down to our definition of displacement. Displacement is the change in position of something according to its starting point, therefore is measured as the crow flies. So for displacement, it's the shortest possible distance between two things. The actual distance that the player travels will not necessarily be in a perfectly straight line, and so the actual distance they travel will likely be a bit larger than the displacement. Probably not by much, but depending on who they're having to run around or any curves in their path, they will run a greater distance than their displacement suggests. So quite simply put, displacement assumes or is a measure of the minimum distance, because it's a direct measurement from one to the other. And the player is not likely to run in a straight line. Okay, as I said, both of those are needed for merits. If you did just one of these parts correctly, it's enough for achieve. But for here, the mark scheme, it just wants you to say they're not running in a straight line, or may not run in a straight line. So no big paragraph needed, just a simple sentence. And that's part B. Now for part C, we're given some more information, this time involving masses. So hopefully your mind is slightly shifting towards momentum and collisions, because we are told that the softball has a mass of 0.18 kilograms, thrown at 44.4 meters per second, and is caught and brought to a stop at first base. If something's stopping, it means its velocity is 0, so it's probably a useful bit of information for a subsequent calculation. We are told that the catcher's arm is relaxed and the ball and padded glove move backwards a little bit once the ball collides with the padded glove, and the ball takes 0.510 seconds to stop. This results in an impulse. For part I, we are asked, what does the term impulse mean? Now, you're not given an equation directly for or explicitly for impulse, but you have to remember for the equation delta P is equal to F delta T, really there is a secret I here for impulse, where your impulse is just the change in momentum, or the force multiplied by the time taken for that force to occur. So easier just to say change in momentum. And that's enough for achieve. As before, if you do any one of these three parts correctly, just having a quick scan, it looks like you can get achieved, and you need multiple ones for merit. Oh, sorry, you need to do parts 2 or 3 for merit. So for part 2, we are asked to calculate the average force on the ball, of the ball on the padded glove on impact. And so our average force is this force from the equation up here. So if delta P from our formula sheet is equal to F delta T, then F is equal to delta P divided by delta T, or change in momentum over change in time. Our delta P is the same as the final momentum minus the initial momentum. And our delta T is the time that's elapsed. That was 0.51. So I'm going to substitute that in straight away into my equation. Now we're not given the momenta of the ball or the catcher, and so we're going to have to find them individually using our equation P is equal to mv. Again, because we were told the masses, it was a big clue that we'd be doing this ourselves. Our final momentum occurs when it has its final velocity. The ball's journey ends when it is stationary, so it's going to finish with a momentum of 0.18 multiplied by 0. Anything multiplied by 0 is 0. So PF is 0 kilogram meters per second. PI is equal to 44.4 times 0.18. I'm going to do that just quickly while I'm thinking of it. 44.4 times 0.18 gives us 7.992 kilogram meters per second. So just that's it. Okay, so now I can put those into my equation. I have PF is 0, so equals 0 minus 7.992 divided by 0.51. So minus answer divided by 0.51 gives me minus 15.67 recurring, and then it starts a big long decimal. Equals minus 15.67. Then I'm going to round my answer minus 15.7, or you could just round it to minus 16, to be honest. But because the question is giving everything in 3 significant figures, I'm going to give my answer in 3 significant figures. You should always try to match what the question gives you. Like this here, we've got 3 significant figures, so my answer should also be to that many as well. Now, if you did part I and part 2, that's enough for merit. You didn't even need part I for merit. If you just did the delta P, the change in momentum, so minus 7.992 somewhere in your answer, that's enough for achieve on its own. Otherwise, we'll get on to part 3, which is the last place you can earn some marks for this bit. Now, we are asked to explain, using physics principles, what the advantages of catching a ball using a relaxed arm and a padded glove are. Now, this is where you can earn excellence. You have to do the previous sections correctly as well. But we'll have a go at part 3 now, because this is one of those really typical written answers, written explanations that come up all the time. So we'll go through it quickly. Now, we're going to refer back to this equation. I'm just going to write it back down here. This equation is the equation for impulse. Sorry, brain fart. Now, in this equation, if you're trying to catch a baseball or softball, whatever game this is, your delta P is going to be the same. The catcher is going to throw it at the same speed, and you want the ball to stop in your hand. So delta P isn't going to be changing. The force that the catcher experiences and the time taken for the ball to come to that stop, to do that change in momentum to 0, can be changed. And that's where we have the two things here. Relaxed arm and a padded glove. While catching with a relaxed arm, so I'm just setting up the question. While you're catching with a relaxed arm, you might, if you play sport, you'll obviously know why you do this. But you can imagine, if you keep your arm really fixed, you tense up your arm and try to catch the ball, if someone's really throwing the ball quite hard at you, and your hand stays still while catching, it will slap and it will hurt a lot. If you have very soft hands, the ball doesn't hurt you as much. There's less stinging, there's less of a slap, you feel less force on your hand. And it's all to do with this changing of time. If you have soft hands or a padded glove, you're making the change in momentum take longer. As this delta t gets bigger, if the overall change in momentum is unchanged, because it is, then in order for this side of the equation to stay the same, the size of the force must go down. And as I say, if you play sports, you know this is how it works, but this is the physical reasoning and the mathematical reasoning why. So while catching with a relaxed arm, the time taken for the ball to reach P equals 0 is increased. As delta P remains unchanged, because otherwise you're telling the thrower to throw much more gently in a competitive game. Obviously, every split second counts, so that's not a viable option really. As delta P remains unchanged, the size of the force must decrease. So as our time increases, if we're saying our delta P stays the same, it means that our force must get smaller. So the time's increased, delta P remains unchanged, so the force must decrease. This results in less pain for the catcher and reduces the chances of the ball bouncing out. Okay. Now, we've discussed the relaxed arm very thoroughly. With the padded glove, it's an identical description. Different reasoning. It's just that the padding on the glove makes the ball take longer to slow down. Again, it makes the collision spread out over a much larger amount of time than relatively unpadded palm of your hand. There's a lot of bones, not a lot of skin in there, so there's not a lot of padding. The padding increases the time again in a second way, and so you increase time and you reduce the force because the delta P stays the same. So again, it's essentially the same description. So I'm not going to rewrite all this again. For a padded glove, sorry, I am, but very briefly. Time taken increases, delta P remains the same, F must decrease. So those are the three key points that you have to make for each one. Now, if you did all this and your parts I and II as well, that was enough for excellence. The key parts to this last section here, for achieve, you had to have somewhere that as T gets bigger, F gets smaller. If you made that statement somewhere, these sort of 3 points together, then that's enough for achieve. If you didn't do the delta P in this section up here, or if you didn't get this correct, meaning of impulse. For merit, you had to either work out delta P correctly. This is a weird mark scheme you can get. Sure. Or explain the effects of catching for both the arm and the glove. So increasing from force must go down as time goes up to including sort of the description for both and why it's a good idea. Now the mark scheme actually does say to reduce the chances of injury rather than less pain, similar meaning. But it also reduces the chance of the ball bouncing out, which is again what they say is dropping the catch. So you do need to actually have the softball implications in your answer somewhere. Altogether though, that's excellent. And that's part C. Now for part D, we are told that later in the game, a 50-kilogram player is moving to the right at speed v and collides with a player of 60 kilograms who is moving to the left at 0.4 meters per second. The two players collide and stick together and move to the right at 2 meters per second after the collision. Now, I know in your paper this will probably have an actual picture in it. I'm going to just draw a quick diagram with two sections, before and after. And underneath, in my actual answer space, I'm going to split up my work just like that as well. Now before, I have a 50 kg player moving to the right with a 60 kilogram player who is moving to the left. So I've got two independent boxes moving towards each other. Afterwards, the two players collide and stick together. So I'm going to draw them as two boxes stuck together. And this guy's 50 kg with a V of V. This guy's 60 kg, V equals minus 0.4, because I always have to the right as positive and upwards as positive. Anything left or downwards will be negative. This velocity is going to the left, so it's negative. After the collision, you're not told what their total mass is, but you can work it out. 50 plus 60 is 110 kg, and they're moving to the right at 2 meters per second, which is again positive. Now, I know I sort of haven't even bothered answering the question yet, because I can see the massive thing at the end. I know I'm going to have to do some calculations. I find that these diagrams really help to set out your working, and I'll refer back to that in a sec. Part I, which physical quantity is assumed to be conserved during a collision? We assume that momentum is conserved, assuming there are no external forces. Okay, that's the one condition required for momentum to be conserved, is that there is no external forces. Now the mark scheme doesn't actually require that, so I guess you don't need to worry about it. But just in case, I would always add that whenever you're talking about conserving momentum or torque. There are no external forces or external torque or resultant torque. Sorry. Anyway, I digress. Part 2, calculate the initial speed of the 50-gram player. Now this is why I wanted to set out my diagram like I have here, because I'm going to have a before side and an after side. Now, due to conservation of momentum, the sum of all momenta before, oh sorry, I'm off the page, off the screen even. The sum of all momentum to begin with must equal the sum of all momenta afterwards. So you can write that in words. You can write all momentum before must equal all momentum after. You just need to have somewhere in there some sort of description of you conserving momentum, because that's the premise that we're using for this problem. And then what that means is we have the P of the 50-gram player plus the P of the 60-kilogram player must be equal to the P of both. after the collision. Okay. Then I'm going to use P is equal to mv to substitute in the mass and velocity values for each person. Remembering that my 60 kg player was initially going left, so will have a negative momentum, because I always do to the right as positive. So you just go through and make those substitutions. 50 times v, the unknown, plus 60 times minus 0.4 must equal the mass of both of them multiplied by the velocity of both of them, which was 2. So again, the way I'm sort of going to lay this out is that I've got this really clear distinction following from the diagram down, that I've got 2 separate things that I'm going to make add up to each other. So yeah, you may not want to do it like that, but I'm going to. I'm just going to go through and simplify these terms. 50v 0.4 times 60 minus 24 is equal to 220. Then obviously I want to get v on its own, so I'm going to add 24. Sorry, I'm going off the edge again. Add 24 to both sides. 50v is equal to 244. Then I'm going to divide by 50 so that I get v on its own. And my last thing is to put it in a calculator. 244 over 50 gives us 4.88 meters per second. Now, before I go any further, it's always good practice to just think to yourself, does this make sense? Particularly with a long question, there's a lot of, individual calculations. After the collision, both players were moving to the right, stuck together with a relatively high velocity compared to what they started with, or at least what this guy started with. He got knocked backwards and he was heavier than the other guy. So just by sort of intuition alone, we can tell that this V is going to have to be bigger than 2, and it's going to have to be positive. Our answer is positive, and it's a little bit over 2, which makes sense given that their masses are very similar. So yeah, that's the right answer. Altogether, that's excellent. If you were trying to do this but made one sort of error, either in the equation you used, the value you used, anything at all, just one error, then that's merit. If you calculated any of these individual momenta correctly, that was enough for achieved, or just stating that we're conserving momentum at any point was enough for achieved. Altogether, that's excellent, and that's question 1. For question 2, we are looking at cornering. We are told that a player has a mass of 55 kilograms, moving at a constant speed of 7 meters per second. They follow a circular path as they round second base. We're still talking about softball. The radius of the circular path is 15 meters. Calculate the centripetal force acting on the player as they round the base. Now, looking at our resource sheet, the formula for centripetal force is Fc is equal to mv squared over r. Now, if you look at the question, we are given a mass, given a velocity, and we're given a radius. So we're just going to plug all those numbers straight in. 55 times 7 squared all over 15. And then just put it in calculator. Oops. And you should get 179.6 recurring, which is the same as 179.66666 forever and ever. Therefore, rounds up to 180 newtons. If you do all that, that's enough for achieved. There's no merit on this question. Now for part B, we are asked to add labels to the diagram below to show the direction of the force, acceleration, and velocity of the player. Now remember, with centripetal motion, in order, I often find that these running ones are a bit hard to imagine than the Earth orbiting the Sun, as an example. So whether it helps you or not, it helps me visualize it. So in space, obviously the only thing that's pulling on the Earth is gravity, and that must be pulling it towards the Sun. So the same thing is true here for our runner. For any centripetal force, there is an unbalanced force. It has to be unbalanced, otherwise it will not continually change direction and therefore change velocity. So there must be a force acting towards the center of the circle. Okay, that's going to be our Fc. Now, because this is an unbalanced system and this is our centripetal force, and we know from Newton's second law that F equals ma, the acceleration must be in the same direction and proportional to the force. So we're going to have a second arrow. It's going to be roughly, so it doesn't really matter on the sizes because that just depends on the mass, but do draw them slightly separated just so the examiner can see that you've got two different arrows. In reality, they are both acting in the same place. We are just doing this so that the marker can see what you're drawing a bit more clearly. And then we've got two of our three things drawn up. Now for the velocity, we know that the person's going to have this circular path, but at any given moment, instantaneously, their velocity isn't circular. It is at a tangent to the circle, which means it's the line that touches the circle just once. And as they experience this force, their velocity is ever changing, which is why there is this unbalanced force. Okay. Now, if you do all three arrows drawn and labeled correctly, that's merit. If you just do two of them correctly, that's enough for achieved. But you do need to have them labeled, so make sure whether you use the words or the symbols, you do have some sort of label to tell the marker which one's which. And for part C, we are asked to name the force that supplies the centripetal force acting on the player as they move in a circle. Now, obviously, the player is not being pulled to the center of the circle by gravity, like with the sun and the earth. The only force that's helping the person turn, same with cars on roads, is friction. Okay, so for cars or people, Fc equals, sorry, this is just a general tip. If it's cars or people, the Fc is friction. If it's strings or ropes or things spinning around, like being whirled around, or like a hammer throw, ropes or spinning is often tension. And then space ones, like I talked about before, is often gravity. Now, I haven't seen any exam problems like this, but if you were dealing with things like atoms, then you may well have the electrostatic force. So those are the sort of typical examples that come up. And these are the centripetal forces, these are the forces that provide the centripetal force. Remember that centripetal force is not a force in its own right. It's just the name for an actual force that happens to pull something towards the center of a circle. So gravity, electrostatic force, tension, friction can all be centripetal forces, but a centripetal force is not a thing in its own right. Okay. Now for part 2 in C, we are going to explain why the player can be moving at a constant speed and yet be accelerating at the same time. And it's sort of what I was talking about before. Speed is not a vector. This is the fundamental point where this distinction comes in. Speed is not a vector, yet acceleration is the change in velocity, which is a vector. And so, speed is not a vector, so direction is not part of. Therefore, the player can have constant speed as they are covering the same distance every second. So you're just making it crystal clear that this speed just means they're covering the same distance per second. Acceleration, then we're going to give the definition of acceleration. So we've explained the difference between speed and velocity, and we've made sure that's why speed can be constant. We've explained that first bit. Now we're going to tackle the acceleration bit. So acceleration is the rate of change in velocity, which is a vector. As the player is constantly changing direction, because they're essentially, if instead of following the person moving around, if we just had the vector arrows, it was changing over time, it would effectively spin around backwards like a clock. Because they're constantly changing direction, their speed isn't changing, but their velocity is. Therefore, they are accelerating. As the player is constantly changing direction, their velocity is constantly changing, so they are accelerating. Okay, now if you answer as I have done, this is an excellence question, sorry, it's not even on the page. I apologize if you might need me to move it up. So for achieve, you had to either give friction as the centripetal force, just name friction as the centripetal force, or you had to give one of the following points: that velocity is a vector, which is this statement here, velocity is a vector, or acceleration is defined as the rate of change in velocity or the change in velocity, or you had to say that speed is constant, but they are changing direction, therefore velocity is, therefore they're accelerating. That's just a bigger point, but the other two, a bit shorter. Any one of those is needed for achieve. If you had two of those points and linked them together, that's merit. If you had said friction and gave this full explanation, talking about speed being just a constant magnitude, but it's still got a change in direction, so it is accelerating, then that's enough for excellence. And then that's part C. Now, part D, we are told that the player runs onto a large, slippery, muddy patch while rounding the base. Describe and explain fully, using physics principles, the effect of the slippery mud will have on the player's motion. Now, I'm going to draw just a very quick arc with this guy's motion on it. So we've said before that he has his velocity here and his force due to friction going inwards. Now, when they run onto a large, slippery, muddy patch, you don't need to necessarily say, there's not a particular, you don't have to say the centripetal force or the friction goes to zero, but you do need to say that, or that the force has got smaller. So if you run onto something slippery, the amount of friction between your shoes and the surface gets smaller, which is why we have less grip, less friction, which is why it's slippery. Therefore, the force goes down, and we can discuss what happens to the motion afterwards. So, on the writing in blue. On the muddy patch, the friction is very small If you write goes to 0, provide 0 newtons, because that will make the rest of the explanation technically correct. This is acceptable, it's not quite true, but there's some sort of minor leeway that you're allowed with your descriptions here, as I'll explain in a sec. On the muddy path, the friction is on the muddy patch, the friction is very small. Therefore, the centripetal force, which is the friction, is very small. Therefore, the player will not turn in a circle. Instead, the player will continue. There's two key points here. One is the direction, one is the size of the speed. Instead, the player will continue the path at a tangent to his original path with a constant speed. So, this is an excellent question. You don't actually need to write that much for here. The key points are that the friction gets smaller on the muddy patch, therefore centripetal force gets smaller. That's enough for achieve on its own. Then you have to talk about the fact that if it's wet and slippery, there won't be enough of a force to turn in a circle. Instead, they will move off either, you can describe it as a tangent, which is what this straight line is here. We'll just move off in a straight line, no longer being turned towards a circle. That's not actually accurate, but it's an acceptable answer, because we're assuming that the friction force will become so small that effectively you move off in a roughly straight line. In truth, you will continue with the original path, but with a much greater radius as the force goes down, because in the equation Fc is equal to mv squared over r. If you're keeping the actual speed and the mass the same and your force goes down, then it means the value of this fraction is getting smaller, so the denominator has to be getting bigger. So the radius has to be getting bigger. And so it may not necessarily be a straight line, but it will be a wider curve, certainly. Now, for excellence, it's a weird mark scheme. It says 2 points needed for merit, the ground being muddy reducing the force, and them not having enough centripetal force to continue in their original circle is enough for merit. For excellence, need full answers. The only additional bit is in brackets, and it says the friction is the centripetal force is provided by friction between shoes and the ground, which we've discussed already. So I don't quite understand where the excellence explanation comes from. So with a complete answer like this, I would imagine this is enough for excellence. If you make one of these sort of points, it's an achieve. 2 of them is for merit. And then that's question 2. And we're on to the last one about projectiles. Now we're told that the next batter hits the ball up in the air with an initial velocity of 22 meters per second at an angle of 35 degrees. And we're given this sort of setup as it is in this diagram handily. We are asked, first of all, to show that the vertical component of the initial velocity of the ball is 12.6 seconds. Sorry, I didn't underline these because they are given in the diagram, but it's always a good idea. So I'm just going to add to this diagram my 2 components. If this is our initial velocity vector, vi, just so it's crystal clear, then this dashed line coming out is our VIH, initial velocity horizontally, and this is our initial velocity vertically, VIV. You ever forget that? Remember, the horizon is sideways, so horizontally is sideways. Vertically is like vertigo because you're tall. So it's the vertical side, the one that goes up. Just think that's useful. We're going to show the vertical component of the initial velocity is 12.6. And so we are going to use the fact that this is a right-angled triangle and SOHCAHTOA in order to work out the missing side. Now the vertical component is of the side of the triangle that is opposite the angle we are given. So we are looking for the op, and we've been given the hip. So we're going to use SOHCAHTOA. We're going to use sine theta is equal to op over hypotenuse. I'm going to rearrange this to get the op on its own. So I'm going to multiply both sides by hip. You may prefer just writing O and H instead. That's fine. I'm just doing it for clarity. I've got my hypotenuse multiplied by sine theta is equal to the opposite side. My hypotenuse is 22. If I sub in my theta, I'm going to sub in 35. And have a go on my calculator. Now, making sure your calculator is in degrees, I'm going to do 22 sine of 35, which gives me 12.61868, which rounds to make 12.6 meters per second. To show that question, so I know my answer is correct, and I've shown both my unrounded and rounded answer. Perfect. Whoops. Now, depending on how you've done this, you may have used the angle 55 up here and done cosine. It's exactly the same answer, just a different way of orienting yourself. Now, for this next part, we are asked to calculate the maximum height reached by the ball above the ground. Now, just to save me moving it up and down, I'm just going to do a very quick sketch showing the path of the ball again. With its initial velocity, VI equals 22, just labelled on there. Okay, now the maximum height from this diagram occurs here. Now, from your stuff in calculus, hopefully you'll recognise this as a turning point. Momentarily, the turning point means that it has a change of a gradient, of 0. If this is our height, then velocity is our gradient. So this is when the velocity vertically is 0. Or you can just think of it as going from positive to a negative velocity vertically. Therefore, for a split second, it must be 0. Either way, the ball reaches the max height. Max height occurs at V equals 0 meters per second. Okay. Now, because we're dealing with the vertical motion, we're going to have to work out the initial vertical velocity, which is handily what we did in part A. So we do not need to work that out again, but we do know our initial velocity vertically. To save having to write V's next to everything, I'm just going to write vertical motion, just so it's clear to me that I'm only considering the stuff vertically. Then I'm going to use my trusty 5 letters laid out, where my maximum height is my distance. So my distance is Hmax. My VI is the 12.618. Remember to use your unrounded answers. My VF is 0, as I just said. Max height occurs when VF is 0. My acceleration on Earth is minus 9.8. I always have gravity as negative because graphs always have downwards as negative. Just means there's less different situations to remember. If you always have down as negative and up as positive, same with the graph, right is always positive, left is always negative. Just means you haven't got to chop and change it. Just keep it the same, makes it way easier for you, and it works every time. Time we don't care about, so we'll just ignore. Now we need an equation that involves these 4 we have VF squared is equal to VI squared plus 2AD. I want to rearrange for D on its own, so I'm going to do that before I do anything else. Minus VI squared from both sides. Then I'm going to divide by both 2 and A at the same time. And just write the D first, giving me VF squared minus VI squared all over 2A. Because I've written down my values, I can then just substitute them all in. 0 squared will just be 0. My 12.618 squared goes there, then 2 lots of 9.8, or minus 9.8, sorry, give me minus 19.6. And then, because, as you should, don't delete your previous answer, you may just have to just save you time having to recalculate it. I can just put into my calculator minus answer squared, rather than having to type out my full decimal, divided by minus 19.6, or 2 times minus 9.8. Either way, you get a height of 8.124 meters equals 8.12 meters. Because again, all our stuff we've been given is in 3 significant figures, so my answer is here. Now, if you got all the way up to there, that is achieved on its own. In order to get merit here, there's one little bit that we have to go back and remember, and it goes back to this initial diagram. We've worked out the maximum height reached by the ball if it starts here, getting up to here. But if you look at this diagram, we're not starting on the ground, we're starting 1.6 meters above the ground. We're not talking about the change in height, and we are talking about the maximum height reached by the ball above the ground. So our H max really is 1.6 plus 8.12 meters, giving you 9.72 meters. Now, just that little extra step takes it from, this extra little step takes your answer from an achieved, which is all of this stuff, to a merit. If you forget the 1.6, it leaves it as an achieve. There's still quite a lot of work to do for that. And that's part B. Now for part C, this is another really typical explain question. We are told that the ball's motion can be tracked and can be shown as the parabola motion below. When we see parabola, all it means is it's this nice curved shape, like a quadratic you'd see in maths. What we use here is that it's symmetrical, and that's significant. I'll explain why in a little bit. Now we are going to use physics principles to fully explain the motion of the ball from the time it leaves the bat until it hits the ground. Add labelled arrows of appropriate length to show the forces or force on the ball at A when it leaves the bat, B at maximum height, and C just before it hits the ground. Now, it's easy to get confused by this, but as it's leaving the bat, it means that the contact has ended. Therefore, the bat is no longer putting a force on the ball. In order to solve these problems at all, we must make the assumption that there is no air resistance. When I said that this parabola is symmetrical before, it's because there is no sideways force slowing the ball's horizontal velocity over time. We only consider the one force, and that's the one that's pulling it towards the earth. Now I'm going to use a ruler here because they should be the same length. It says appropriate length, so that it's going to be checked because gravity doesn't get noticeably weaker unless you go a very long way up in the atmosphere, which this ball is not. It will have the same sized force at each 3 positions. I'm making mine a centimeter each just because no real reason for it. Then I'm going to say that this is my weight. And to be honest, W or FW would probably be fine as well. So that's part I. If you do those 3 arrows pointing downwards the same length with the same labels, then that's achieved straight away. If you don't do that, you can get achieved from these bits down here. Now for part 2, describe and explain how the forces, acceleration, and horizontal and vertical velocities of the ball change throughout its flight. So if we do 2 of these statements correctly, that's enough for achieve. If we link together the force, acceleration, and velocity for either velocity, then that's merit. And then if we do everything perfectly, then it's excellence. Now, the force part follows on nicely from the arrows we've just drawn. We've said the force on the ball remains constant. It is solely due to gravity, so has the same size and direction at all times. So it sort of feels like I'm over explaining it a bit. You need to have in your answer at some point that there's only a vertical force and that it stays the same. So because I'm saying it's solely due to gravity, we know that it's solely acting downwards. There's no horizontal component of gravity. And I've said that it's constant, and I've over-explained that last bit. That's the amount of detail you need for a successful reasoning, or not reasoning, explanation of forces. Now for acceleration, because F is equal to ma and m is a constant, the acceleration will have exactly the same description as the forces. Acceleration due to gravity will remain constant. There is no horizontal acceleration Same meaning as the first one, worded slightly differently. Both are acceptable, both is correct. Both have the same pattern. Now, horizontal velocity's description is a consequence of this last point I've made. There is no horizontal acceleration. This is a really key sentence to have in these sort of answers. Because there is no horizontal acceleration, because AH, short for acceleration horizontally, equals 0, the horizontal velocity will remain constant. Now the mark scheme references unlinked and linked statements. I've linked the statement to the acceleration in saying that this is why the horizontal velocity is a constant. If you just say it stays constant without explaining that the horizontal acceleration is 0 in either part, then you can't really get into the merit bracket for that. So this linking between parts is necessary for merit and certainly excellence. So far we said that everything's staying the same, but at last we get to something that does change, and it's the vertical velocity. Vertical velocity, sorry, I'm going to refer back to the diagram up here. The vertical velocity begins in an upwards direction. Momentarily at B, it becomes 0 before becoming increasingly negative. So the vertical velocity starts, and if you know the value that it starts at, it's always good to give it, starts at 12.6 meters per second. I'm going to be crystal clear in saying upwards as well. At point B, this is reduced by the acceleration due to gravity, again, linking it to my acceleration statements. At point B, this is reduced by acceleration due to gravity to 0 meters per second. At that very apex of the curve, at the zenith of the curve, we have 0 meters per second of vertical velocity. Then the VV or vertical velocity becomes increasingly negative, because the negative is just directional, until it hits the ground. Now this question's slightly different to how this description stuff usually comes up, in that there was a difference in starting and finishing height. Because the ball started in someone's hands about 1.5 meters above the floor, it's going to fall slightly and hit the ground slightly faster than it left the bat, because it's got that extra 1.5 meters to accelerate downwards. So it ends with a larger speed than it started with. Now, this comes as sort of in the mark scheme as well in brackets, so I'm going to put it in brackets as well. This isn't necessary for the answer. This is unique to this situation. Most times it will not involve this last section. Everything else here is basically the same for any problem that comes across like this. There is no horizontal acceleration, there is only vertical forces and acceleration, therefore horizontal velocity stays the same. The vertical velocity starts off positive, becomes 0, then becomes negative. That change from positive to 0 to negative has to be described explicitly. If you know the starting speed, it's always a good idea to give it. If you don't, just say it's positive, then becomes 0, then becomes negative. Okay, just as if you're describing the gradients of a curve in maths. Okay. Altogether, if you have got these linked statements in there, it's excellent. If you got these arrows wrong, but still linked together the force, acceleration, and one of the two velocities, then that's merit. If you made two correct statements but didn't link them together, so just saying acceleration due to gravity will remain constant, and the horizontal velocity will remain constant, if you just say those without the linking bits, it's just achieve. We need two unlinked ones for achieve, not just one. Alternatively, if you just did the arrows correctly, that was enough for achieve as well. They had to be labeled though. Final part, part D. We have a 110 kilogram coach and a substitute player of mass 74 kilograms sitting on a uniform bench. The very last question there, snuck in talk. It seems a little bit mean, but hey ho. 110 kilogram coach, the player of mass 74, and the mass of the bench is 40. I'm going to underline uniform because that's an important piece of information. On the above diagram, obviously we're missing ours. Add arrows to show all the forces acting on the bench. So I'm going to do my best to infer where everything is based on the bits of the diagram that are left. We've got a supporter A, because we're told that down part 2. We have our bench going across. It looks like it's about that length from arrow to arrow here. And we've got coach sat, I presume 0.35 away. So I'm going to look at the mark scheme. Oh, because it does have the actual diagram in there. If you're unsure, have a look at the mark scheme to get the full diagram with the pictures included. Mine's not neat enough to do the same from. So important to note, the coach and the player are not sat on the support points. They're not sat at either end. They are sat just off the end and just to the side of each support. Now I'm going to start adding in information. Now I'm going to label on the forces acting on, because the question asked me to. I'm going to write it as 110 G because weight equals mass times gravity. So this is not 110 grams. This is the size of the force, 110 times 9.8. Likewise, for the player over here, this is 74 G. You can just label it with weight as you see fit, or you can actually work out the value of it. Go for your life. The other two forces we have, at the moment, we're suggesting that this bench is sinking through the supports into the floor. That's not the case, it's balanced. Pardon me, sorry. So there must be two forces here, a support at A and a support at B. Okay. Now, the question asks us that by calculating torques around support B or otherwise, determine the values of the support forces at A and B. Before I do anything, I'm just going to write down the two rules that I'm going to make. For equilibrium, it's always a good idea to set out your own physics rules. For equilibrium, there are 2 points. Torques must be balanced. Forces must be balanced. Now, what that means is, for torques, our torques, the sum of all torques going clockwise, must equal the sum of all torques going anti-clockwise. If you aren't familiar with the sigma sign for summing, just write the words all torques clockwise must equal all torques anti-clockwise, in the same way that all forces upwards must equal all forces downwards. So straight away I've set out my rules, and these are the two principles I'm going to use to solve this. Now, my torque equation is equal to the force times the perpendicular distance to the support force. Because the question is suggesting I do it this way, I'm going to say that B is my pivot point. So I'm just going to draw a big circle on it and say pivot, just to make it clear for me and the examiner as to what I'm trying to do. So whenever I'm working out a torque, it's the distance measured from that pivot point, from the support force at B. Now, I need to work out all the torques acting clockwise and all the torques acting anti-clockwise. Now, I feel if you struggle to do this conceptually, my suggestion for you is to get your pen, pencil, ruler, whichever straight object you have to hand, put it on the thing that's experiencing all the forces, in this case, the bench. Put your finger down wherever your pivot point is. Mine's here. My finger's going there. Now, to work out which forces are going to turn the bench clockwise and anti-clockwise, let's say I'm looking at this 110 G, the weight of the coach. I'm just going to pull the pencil down in that direction of the arrow while holding the pivot point steady. And so I know that clocks don't go this way. This is an anti-clockwise torque. So immediately, my torque of the coach, or the 110 guy, is anti-clockwise. Now, something that I've forgotten to do, and just realized it now, is that we were told that this is a uniform bench. So the bench itself has a mass. Because it's uniform, that mass acts through the center of the bench. Therefore, if my bench is 1.5 meters long, my weight of the bench, 40 G, because we're told the bench is 40 kilograms, is 0.75 meters away. Forgive me. It's easy to miss that stuff, even if you're used to doing it. This is our pivot point. Now we have this other smaller torque turning the bench anti-clockwise, but it still is turning it anti-clockwise. So we're going to have our torque of the 40 kilogram bench. Then there are no other forces that are going to spin this bench anti-clockwise. Our support force at A is going to turn it clockwise, and the mass of the 74 kilogram player is also turning the bench clockwise. So I have my tau of A plus my tau of 74. Tau being this curly Greek letter for torque. Okay. So now I can just substitute in my FD for each of those torques. My torque at support force A is the size of the force SA multiplied by the distance. Now the distance from the pivot point to SA is this distance here, from B to A, 0.6. And my torque due to the 74 kilogram person, if we look here, our pivot point is here, our 74 kg person's acting here, which is 0.42 meters away. My mass was 74 lots of G, my distance 0.42. Then I did the same thing in my other two torques, but this time coach is a long way away from the pivot point. He's that 0.6 meters again, plus an additional 0.35. He's not sat at the very end, he sat just before the end. So we do 0.6 plus 0.35, which is 0.95. So 110 G times by 0.95. I'm just writing them in two separate brackets to show which one's the force and the distance, respectively. If you would rather do it just as a time symbol, then that's fine. But yeah. Then I have my torque due to my 40 kilogram object, the bench itself, sorry. The force is 40 lots of G. The distance from the pivot point to the center point is halfway between the two, 0.3. Because this is a symmetrically set up bench with 0.4 and 5 on either side, the midpoint of the bench must be midway through this 0.6, which is 0.3, sorry. So plus 40G times 0.3. Now I've got lots of terms. Often the mark scheme will give you credit for calculating one of these torques, and the same is true here. If you're not confident on these sorts of questions, calculate a torque. Work out one of them. Say T 110 is equal to whatever that's equal to. I'm confident I know what I'm doing, so I'm not going to work them all out individually. In theory, the more calculations you do individually on a calculator, the more chances of making a typing mistake there are, and it also just takes more time to do it. So if you keep it all uncalculated and just do it all at the end, often it's quicker, but you can get an achieved mark for this question just by working out any torque. So if you're in doubt, just work out one of them. It has to be correct, but yeah. So that being said, I said at the start that the sum of all my torques anti-clockwise must be the same as all my torques clockwise. Therefore, all this expression must be equal to the bottom one. So 0.6 SA plus 74G times 0.42 is where you might want to work them all out if you were keen. But I'm going to say that these are equal to 110G times 0.95 plus 40G times 0.3. Then I want to get the SA on its own, so I'm going to subtract 74G times 0.42 from both sides, giving me 0.6 SA on its own equals, I should write it all out, I'm going to. Sorry, I'm trying to write it quick. It gets messy, I am sorry. 40G 0.3 minus 74G 0.42. There might be people that will tell you that now you can collect up your like terms in terms of G and simplify it before doing anything else. Again, it's just more effort. I'm then going to divide it by 0.6 to get the SA on its own. So SA, sorry, is equal to all of that over 0.6. I'm not going to type it because this is a long video as it is. You should write out each step of your working without exception. I'm going to type this all in. 110 times 9.8 times 0.95 plus 40 times 9.8 times 0.3 minus 74 times 9.8 times 0.42, all divided by 0.6, should give you 1,395.1933 newtons. Rounded to three significant figures, 1,400 newtons. Okay, because the 5 is our fourth figure, it rounds the 9 up. So even to three sig figs, it's still just 1,400 newtons. And that's SA. Now, if you wanted to work out SB, you have two options. One's quicker than the other, but one, if you did this bit correctly, is essentially doing it again, but instead of measuring from the pivot point here, you measure from the pivot point at A. You do exactly the same thing, just with slightly different distances and slightly different ways round. The other, quicker way is this forces must be balanced idea here. I know that this bench is not flying up in the air nor sinking through the floor. Therefore, the forces upwards must be balanced with the forces downwards. I've just worked out one of the forces upwards. I know there's one more, and I know the three forces acting downwards. Therefore, I can say that F up is equal to SA plus SB, which we've just worked out to be 1,395 plus SB, and I know that F down is equal to 110G plus 40G plus 74G. Now you could collect up your like terms if you're dead keen. Long and short of it is that because my F's up must equal F's down, I have that 1,395 plus SB is equal to 224 lots of 9.8. Therefore, SB is equal to 224G minus 1,395. And then I can put that in a calculator. Check my answer is still correct. It is 224 times 9.8 minus answer gives me 800.006 recurring. The three sig figs is just 800 newtons. Now, because my working's got a little bit messy and congested, I'm just going to make it crystal clear where my two answers are. You can do that with colours, however you see fit. Now, altogether, that's an excellent question. There's a hell of a lot in there. If you do this second part, the second support force, by resolving torques again, just with a different pivot point, you'll get the same answer. It's just a lot more writing, it's a lot more fiddly, and a lot more chance for mistake. Just resolving the forces vertically is much cleaner and much more likely, less error, less chance of making a mistake. However, it relies on your first answer being correct, obviously. Now, if you get one support force correct, like SA, or if you'd worked out SB first, that was fine as well. That was enough for merit. If you tried to do all this but made one error somewhere through here, like one negative symbol, one number incorrect, and missing 9.8 somewhere, then you can still get merit even if it affects all your other answers. Both of those are dependent on having a correctly labelled diagram up here. Now, I forgot my 40G when I first was doing it, which shows how easy it is to miss those sorts of things. But yeah, if you're ever told that the bench has a mass or the object across the two supports has a mass, it has its weight acting in its center. If it doesn't tell you it's uniform and there's no distance given for the center of mass of the bench, then you assume it is uniform. But usually it will say that, or it will tell you where the center of mass or the weight acts through. For achieve, if you had the 5 arrows not necessarily labelled, then that was enough for achieved, or if you had worked out any talk, like I said. Altogether, this was an excellent question, and that's the 2023 paper.